Hello everybody, we're live here at the Creation Museum Science Lab. I'm Roger Patterson and I'm going to be doing some demonstrations of science ideas and activities for you over the next couple weeks as people are homebound and looking for interesting things to do. As you've probably heard, the Creation Museum and the Ark Encounter have closed to help prevent the spread of the coronavirus. So we're doing these things to encourage you as a family to be engaged. Okay, so if you look here at the table, you see this brown bottle. Probably familiar with what that is. That's hydrogen peroxide. But why does it come in a brown bottle, might be your question. If you think about something like rubbing alcohol, it's in a clear bottle. So why the brown bottle for hydrogen peroxide? Well, it is a photosensitive. So if you can imagine what that means, it undergoes a chemical reaction when light shines on it. And that is a decomposition reaction. So if we could look at an individual molecule of hydrogen peroxide, it would look like this. It has the chemical formula H2, represented by these little white balls, O2, represented by the little red balls. So this hydrogen peroxide molecule undergoes decomposition and it forms a water molecule and oxygen molecules. Now we'd have to balance the equation and think about how all these pieces work together exactly, but that's the basic idea. So we're going to talk today about the reaction of the decomposition reaction of hydrogen peroxide and look at it in detail. So here in this set of test tubes, I've got a mixture of a little bit of food coloring so that you can see things happening a little better, and just the standard hydrogen peroxide that you buy in the store. This is about a 3% concentration, so it's not very concentrated. It's diluted down quite a bit. And we'll look at another concentration here in just a minute. So inside of these test tubes, right now, because light is shining on these test tubes, it's undergoing this decomposition reaction. All right, so can you all see the bubbles forming inside of this test tube? Oh, no, you can't, because it's happening so slowly that you don't really see anything happening. So inside of this test tube, we're going to use it as our control, and then we're going to use these other test tubes to look at how we can speed up this reaction. So here in this little dish, I have a substance called manganese dioxide. All right, manganese dioxide is a black powder, and I'm going to add a little bit of that to this second test tube, and it's what we call a catalyst. It's going to speed up the reaction and it's going to cause that decomposition reaction to go just a little bit faster. So if you look there, you can see the bubbles starting to form, little gas bubbles coming up there, right up to the top. And if I held it over here to the microphone, you probably hear that fizzing sound just a little bit. Hopefully that wasn't too loud. But you can see that reaction sped up quite a bit. Okay? It's happening much more rapidly. It's happening in this test tube, but we can't see any bubbles. So that catalyst helps speed up the reaction inside of this test tube. Now, another substance we can use to do that is called potassium iodide. And it's these little white crystals in this container. Okay? And we're going to add a smidge of that to test tube number 3. And see what that does. And as those go in, you probably start to see the bubbles forming there, and it's fizzing up. And we don't have the black color in there, and they're not increasing the surface tension at all, but this reaction's going quite quickly down there in the bottom of the test tube. Okay? One way we can test to see if this is actually oxygen forming in here is called the Splint Test. So I'm going to take a little splint of wood and we're going to light this on fire because chemistry is much more fun with fire. We're going to let it burn for a second, and as you know, oxygen is required for a fire to burn. So if I blow this splint out and stick it inside of this test tube, it will reignite. Not enough oxygen to ignite, lots of oxygen down inside the tube, causing it to reignite. So we have positive proof that the gas that's being liberated there is actually oxygen. Another thing you'd notice if we had super special cameras is this test tube is getting warm to the touch. Okay, so we'd say this is an exothermic reaction. It's giving off heat. Some reactions require heat to be added in for them to go, so they are endothermic. Okay, so we've got reactions happening here, we've got reactions happening here, and we've got nothing happening still in this test tube. So what we're going to do here, we're going to add a touch of something you've all got around the house, of dish soap. Now, the job of the dish soap in this test tube is to help increase the surface tension of the liquid. So it's going to give us an increased surface tension. And what that's going to cause to happen when we add the bubbles, we'll hope this doesn't get too messy. We'll clean it up if it does. When we add the bubbles into there, we get that reaction going. And you'll start to see it growing and swelling out of the tube because the bubbles can't pop. The soap is binding the bubbles together, and so they're not popping like they are in these tubes. And so it's slowly increasing. And if we let that go too long here, we're going to have a bit of a mess on our hands. And we'll actually be doing this one in a little bit higher concentration and a bigger container in a few minutes. But we're going to set this one aside so that it doesn't make too much of a mess over here for us. Okay, so let's look at something else now. We used the red ones. In these I've put a higher concentration of the peroxide. In these we have 35% concentration, so this is a much more concentrated solution of the hydrogen peroxide. This is not stuff you can buy in the grocery store. It's typically used for cleaning commercial surfaces and things in kitchens and that type of stuff. So much more concentrated. You always want to work with gloves and glasses when you're handling this, so when I prepped these, that was the case. So again, we have the 35% solution here as our control. You can't see any of the bubbles, but I promise you if we could go down to a molecular level, that decomposition reaction is happening. So let's add the manganese dioxide to this one. Now let's make a prediction. If it's a higher concentration, we would expect that the reaction might be a little bit more vigorous. And there we see quite a dramatic reaction. Okay? And again, I'm hearing a lot of sizzling, we've got a lot of bubbling, and since this is a higher concentration, it's going to heat up quite a bit more rapidly. So that reaction, because it was more concentrated, happened much more quickly. So concentration increases the speed of reactions. So let's try the same thing with the potassium iodide, and we'll drop that into the 35% solution. And you can see a much more vigorous reaction happening there. Okay. We'll catch some of that with a paper towel. Okay. And you might notice you can't see my face anymore because there's a lot of steam moving around through the air. Okay. So this is an extremely efficient demonstration of the exothermic nature. I can hold my hand over here and this feels very warm to the touch. So we get a very vigorous reaction out of these because they're very concentrated. The other ones, only a 3% solution, not quite as fast of a reaction. So we can control the rates of reactions if we increase and decrease the concentration. So this might get a little crazy and we'll probably have to grab a couple extra pieces of paper towel here, but we're going to try this with a touch of the dish soap in there to increase the surface tension. All right, we're going to throw a couple more paper towels under here to catch some of this. It's going to be a little bit messy, but messes are fun. Did you hear that, kids? Messes are fun. Tell your parents. Okay, so when we add our potassium iodide to this test tube, I'm going to go a little bit lighter on this one. Okay. The surface tension's there, and it's going to make this foamy substance. Now again, the foam that we're seeing, we saw that in the test tube with just the potassium iodide, but that foam that we're seeing is because the air bubbles are being trapped by the soap. It has a higher surface tension. And again, we've got the steam coming off here. So the water molecules that are being liberated from that reaction are actually evaporating off. There's so much heat, they're evaporating off as steam. Okay, so we've got a nice little demonstration of here how the concentration really affects how quickly the reaction happens. Okay, so one area this is very useful, and not just to make fun stuff bubble up in a test tube. If you think about the way your airbag works in your car, your airbag has to ignite very quickly and generate a lot of gas very rapidly. Oh, there's a little bubble. Pop. We popped it. Okay. So it has to generate a lot of gas very quickly so that that airbag can inflate around you. So using an electrical ignition and a chemical reaction with that catalyst present at a high concentration, it rapidly inflates to protect us in automobile accidents. So understanding things like concentration and catalysts and how those work is more than just making fun bubbly stuff. There's another bubble. Pop. Right? It's about doing real things that can benefit us in real life and solve real problems in chemistry. Okay, so this was kind of fun, but it's little and it didn't make much of a mess. What if we did the same thing in a beaker this size? So we're going to go outside to do this one. And what I've got here is the same 35% solution. Added a little bit of blue food coloring just for fun to give it some color. We're going to take this outside and we're going to try to add our potassium iodide solution, and we're going to see if we can get a little bit more dramatic reaction out of this one. So if you visited the Creation Museum, we're out on the patio. The waterfall steps are over here. The lake's back behind me. Cafe's up above us on the table. And we're going to do this reaction. I'm going to dump this whole bundle of the potassium salt into here as the catalyst to start this reaction. And then I'm going to get out of the way. I've also necked down this nozzle a little bit. So we're going to dump this in here. Going to give it a little swirl, and I'm going to get back. So you can see the reaction happening very rapidly, and then at some point it'll pick up dramatically. And we get this huge pillow of nice blue foam, and you can see the steam rolling off of there. And we've got lots of warm air in here. If I stuck my hand in there, I'd probably get burned. I think we scared the geese off the pond over there. But just an example of how quickly we can make those reactions go and increase the rate of reaction with the concentration, adding that catalyst, and creating these gases that we can use for various purposes. All right, I hope you've learned a little bit about things today, thinking about decomposition reactions and how concentration and catalysts work and affect us. We'll be doing more of these Facebook Live events through the day. At noon, we'll have a speaker, at 3 o'clock, and then at 7:30 this evening as well. So keep an eye on the webpage for all of those pieces. And we also are offering a discount on our website for you to take advantage of our resources during this time where you might be locked up at home, fewer things to do, travel restrictions, those types of things. You can go to the website and there'll be more information about a coupon code there for you using coupon code Matthew6 as a way to get that discount. So look for that information. It'll be posted throughout the day, and more information to come. Again, I'm Roger Patterson, and it was a great pleasure to be with you today. I hope you've learned something about God's creation and how He's created these chemicals in predictable ways, and thank you for being with us.